Hey physics students, this is Dr. Brenzy here, and this is lesson 6.1.3. And our objective for this lesson is that we're going to be able to calculate key properties of the orbits of planets and comets around the sun. I want to give you a little bit of background information about how we came to learn about the motion of planets and things in the solar system. Well, there are two big names. First of all, the guy on the left, his name was Tycho Brahe, and you can tell he lived in the middle of the 16th century, or late in the 16th century. Now, he was a Danish guy, so he's from Denmark, and his big contribution is that he was very, very good at making observations of the position of planets as they went across the night sky, and he was very, very meticulous. He had an observatory that was built with funds from the King of Denmark, and with that, he was able to really pinpoint the positions of planets like nobody else could before. So he had all of the measurements that were necessary to find out some really breakthrough things about the planets and how they work, because there were some crazy ideas out there before these two guys came along. Well, later on in Brahe's life, he met a German mathematician, who's the guy on the right. His name is Johannes Kepler. And Johannes Kepler, he was a pretty brilliant guy. Now, Brahe, he had a hard time actually figuring out what his data meant. In other words, how could he fit his data to some mathematical formula that made sense. But Johannes Kepler, he had the mathematical background to actually take Tycho Brahe's data and actually figure out, okay, well, it seems like the motion of the planets works like this. And he came up with 3 laws of planetary motion. And those 3 laws we actually still use today. So we call these laws the Keplers laws of planetary motion. So he came up with 3 different laws. Now, one of the breakthrough things that Kepler figured out is that the planets don't actually travel in a circle. That was revolutionary. And it turns out that Kepler was able to figure out, using Tycho Brahe's data, that planets actually travel in an ellipse around the sun, and the sun happens to be at one focus of the ellipse. Now, that's some math an ellipse is a mathematical shape, and you can actually create this mathematical shape by sticking 2 push pins into a piece of paper, or I don't know, a piece of paper or something, like cardboard or something like that. So you have 2 push pins, and then you take a loop of string, just a continuous loop, and then you take a pencil and you stretch this string out as far as it'll go, and you do that all the way around, and the shape that you end up making is called an ellipse. These tacks that you put into the cardboard are called the foci, or each of them is called a focus. So the sun is at one of these points where you would put the tack in the cardboard. Well, the fact that Kepler was able to come up with this says a lot, not only about his mathematical genius, but really says a lot also about how precise Tycho Brahe's data were, which was really amazing. So without both of those guys, we wouldn't even be able to figure this out. Well, we might have figured it out eventually, but it would have taken a long, long time. So that's Kepler's first law of planetary motion, and that's kind of the mind-blowing thing, is that, wow, we actually are traveling in an ellipse, not in a circle we are so used to seeing. Well, here's the second thing that Kepler found out. It turns out, and it turns out that he calculated that when a planet travels around its ellipse, that it sweeps out equal area in equal time. So what does that mean? So let's say that our planet starts off right here at P1, and in a time t, it moves over here to P2, let's say in a month or something like that. I don't know if it's actually a month or not, but let's say it's a month. So in a month, it goes in its orbit from here over to here. Well, the area that it has swept out in that time is given by this area in blue here. Well, if you go later on in its orbit and you still go from 1 month to next, so we start here and a month later we end up right here. Well, it turns out that now it has swept out a different area, but the crazy thing is that Kepler was able to figure out that, hey, the area of this thing is equal to the area of that thing. Okay, now that seems like really impractical, but if you notice, there's something that happens as a result of that. Let's put it this way. This distance is a lot bigger than this distance here. Okay. So when a planet is closer to the sun, it is going to travel more distance over the same amount of time than it would if it's farther away from the sun. So a planet, when it is closer to the sun, is traveling faster than it would be when it's farther away. So that's really the thing that you really want to take away from the second law of planetary motion, is that when you're closer to the sun, you end up going faster. When you're farther away from the sun, you end up going slower. Okay, there's a third law of planetary motion, and probably the best way to describe this is by actually using this equation. Okay, so this equation says that if you have two planets going around the same sun, that if you take the ratio of their periods, in other words, a period, if you remember back from circular motion, is the amount of time to go all the way around and back to your original spot. So period is the time of one orbit. Let me write that down. So it's the time of a complete orbit. Yeah, that's a bad look in our orbits. All right. So in the case of the Earth takes 365.25 days to go completely around the sun. So we would say that the period of Earth is 365.25 days. So it is a time. And there are times of other planets that other planets take to go around the sun, and you can get that from that table of data that you got in lesson 6.1.1. Well, what is this R thing here? This R is what's called the semi-major axis of the orbit. So if you were to pinpoint the center of the ellipse, so let's say I'm going for planet B, and let's say that for planet B, this is the center of its ellipse. Well, it turns out if you draw a line from the center of the ellipse out to, whoops, I'm not drawing for some reason. If you draw a line from the center of the ellipse out to its edge along the longer part of the ellipse, the longest part of the ellipse, well, this distance from the center out to here is what's called the semi-major axis. So if you take that semi-major axis, if you take its length, and you find the cube of that semi-major axis, and then you have another planet, planet B, and you take its semi-major axis, well, the ratio of those two semi-major axes cubed is equal to the ratio of the periods of the two planets, the ratio of the squares of the periods. And you're like, wow, this is like a complicated equation. So I think I'm going to actually show you an example in class when you get back, when we next meet. But for now, I want you to just know what this formula is. Another way of saying it is that the square of the period is proportional to the cube of the semi-major axis. Now that's pretty deep stuff, but there's one nice thing that will help us simplify Kepler's third law, especially a little bit. Because for planets and moons, the ellipse is almost the shape of a circle. Okay. Now this, you could say, looks like a circle, but it's actually an ellipse. And its ellipse is, it's an ellipse that is like so close to being a circle that it looks like a circle. So in this case, instead of talking about the semi-major axis, if I can draw this correctly, we would just think about this as the radius, r. Okay, so Kepler's third law says that if you have two planets, Ta, if you have the period of a second planet orbiting the sun, like say Mars, and you calculated the ratio of those two periods, and then you took that squared, that would equal the radius of planet A's orbit over the radius of planet B's orbit, and you would take that to the third power. This value you can get for each planet from your table, the radius, the average radius. So you would find the radius of the Earth's orbit, plug it into here. Then maybe you have another planet like the planet of Mars. You would plug that Mars's radius there. And then you'd find out, well, the period of planet Earth, that's 365.25 days. And the radius of Mars is something like, it turns out to be about, well, I'm not going to even guess. I better look it up from the table. So I tell you what, I'm going to give you an example. All right, let me give you an example of Kepler's laws of planetary motion, especially the third law. All right, so let's go through an example here. So let's call this example. All right. I started explaining this, and I might as well just go ahead and show you an example. So let's call this example. Okay. So in your table, and I need to bring my table up. In your table that you saw in lesson 6.1.1, I'm going to pull some things from that table. And by the way, I'm going to give you a nice copy of this tomorrow, so that you always have it with you and you can quickly refer to it, because we're going to need it throughout this entire unit. Okay, so we know that the radius of Earth, actually, let me do this. Let me do it as a table. So we have the radius of the planet's orbit, and we have the orbital period T. And you can get both of these from, yeah, that's not a nice looking T. You can get both of these from your table from lesson 6.1.1. And let's see, we're going to compare Earth with the orbit of Mars. Okay, so if we take Earth and we're going to find its orbital radius, it's going to be 1.5 times 10 to the 11 meters. Okay. And Mars, its orbital radius is 2.28 times 10 to the 11. All right. The orbital period of Earth is, like I said, 365.25 days. Your table says 365.3 3 days. And then the orbital period of Mars is 687.0 days. All right. And let's see, we're going to call for our formula, Kepler's third law formula, we're going to call this planet A. So planet A will be Earth and planet B will be Mars. Okay. Now it said, Kepler's third law says that if you take the ratio of the radii, it's actually semi-major axis, but remember planets are in close to circular orbits, so we would use the radius. And if we take that to the third power, that's going to equal the ratio of the periods raised to the second power. All right, well, let's use that formula and plug in some values. So let's take let's see, RA divided by RB. The ratio of the radii is 1.5 times 10 to the 11 divided by 2.28 times 10 to the 11. And it turns out that when you take that ratio, oh, where did I put my calculator? No, I have one right here. That number's probably going to be somewhere around 3/4. It's going to be a little bit less than 3/4. I'm guessing it's going to be around 0.7. So 1.5 times 10 to the 11th divided by 2.28 times 10 to the 11th. I get 0.657. Okay, 0.657. Okay, now let's take the ratio of the periods. Well, the Earth takes 365.25 days to orbit, go around the sun, and Mars takes 687 days. Okay, so when we find that, we get (0.532). All right. So if Kepler's third law is correct, I can take this number let's see here. Let me back up because I've already written the law up here. So I can actually take this number, that number right there, and take it to the third power, and that should equal this number raised to the second power. All right, so let's test that out. Let's see if 0.657 raised to the third power is really equal to 0.532 raised to the second power. All right, well, that's 0.657 raised to the third power. Let's see, little hat, 3. And when I hit enter, I get 0.284 on this side. And then when I do this, when I evaluate that thing on the right, so that's 0.532, and I just have to square that, I get, 0.283. Oh my goodness. All right, so somewhere along the way, I got a little bit of a rounding error. All right, but I hope it demonstrates to you that it's very, very close, if not equal. So, Kepler's third law really does work for Earth and Mars. Okay. So sometimes what you have with Kepler's third law is you might know 3 of these things, and you have to figure out the 4th one. So you might need to be ready to take square roots. You might even need to take cube roots every once in a while. So depends on whether you're an advanced or AP. All right, class. I look forward to seeing you tomorrow, and I'll look forward to also talking to you about Kepler's law and orbits and doing some work with those. Have a good evening. Bye.